Coming back to the manganese electron configuration, we can also here identify the quantum numbers. For example, for the electron in the 3d5, one of the electrons in the 3d orbitals. So we can first draw the d orbitals that we represent as 5 squares, like this. And we can fill now these orbitals with 5 electrons, like this. So the n obviously is 3 because this is the number of n. And the L, d orbital, corresponds to L equal to 2. Okay? While the ML, in this case, it could be -2, -1, 0, +1, and +2. So any of this would be correct for the electrons in 3d5. Now the MS normally is either plus half or minus half. What's important is if you fill the electron first with spin up or plus half, then the rest of the electron should also be filled in spin up condition. Because first it needs to fill all the empty orbitals with the same spin. You can also write it down like this. If you start from spin down, that also works, but you all have to do it then like this. Yeah, the spin has to be the same until you have to pair them up. But in this case, you don't have to pair them up because it's 3d5, so you have 1, 2, 3, 4, 5. So the n is 3, the L is 2, the ML could be -2 to +2, and the MS could be plus half, all of them, or minus half for all of them as well. The arrangement of the electrons in the orbital also influences their magnetic property of the atom. When all of the electrons are paired, for instance in 3d10 like this makes the total spin amounting to 0 because you have 5 plus half, and you also have 5 minus half. All right, and for atoms with such configurations where you fill in the orbital and there is no unpaired paired electron, this will cause the atom itself to be a diamagnetic. Okay? On the other hand, if you have unpaired electron, for instance like this or like this or like that, still you have, in this case, 1, 2, 3 unpaired electrons. The total spin now is, of course, not 0. And therefore, we call this type of elements the paramagnetic. Now, although the way we fill the orbitals, we start from 1s. We start from 1s, and then when we arrive to 4s, we start first with 4s and 3d5 because 4s has a lower energy level compared to 3d. But when we try to make an ion out of this, say we want to make the Mn2 plus and we want to write down the configuration for electrons in Mn2 plus. In this case, if we write 2 plus, that actually means this manganese now is lacking 2 electrons, meaning 2 electrons would have to be released from the manganese. And the 2 electrons that would be released, we start from the one with the biggest N. As you can see, from 4s to 3d, the electron will actually be taken out from 4s. So the configuration for Mn2 plus would be Ar3d5. And if we want to take out even more electrons, say we want to make Mn4 plus, then we take 2 more electrons, so we end up with Ar3d3. You can also work backwards. So if you have an unknown ion of X2 plus and the electron configuration is Ar, say 3d6, that means for X is actually Ar, and you have to add 2 electrons and you add them in the 4s2, yeah, because the electrons that were released were from the highest N number like this.